So for today's presentation, the outline goes like what is machine learning, what is linear regression. Please respond. Can you identify who the person is? I mean, yes or no? Hello, someone please respond. No, right? Okay, fine. So we are not able to identify who the person is, right? Because none of the information about this photograph is stored in our brain, right? That's the reason we are not able to identify who the person is. But at the same time, when you look at this image, we can easily identify that this is Dr. APJ. Because day by day, hearing about him, looking at his photographs, then videos, and hearing his voice, our brain is well trained with all these kind of features. That's why our brain is quickly able to identify that this is Dr. APJ. Actually, this image is the childhood image of Dr. APJ, right? And when you look at the next image, and here too, his face is visible, even his head is covered with a cap in the left side image. And you see his this portion of his face is visible and some of his hairs are also visible. Even looking at this image, we are able to identify that this is Dr. APJ. At the same time, when you look at the right side of the image, his head is entirely covered with a helmet. Only a small portion of his face is visible. Even then, we are able to identify because our brain has collected that much of information about him and it is well trained to recognize that this is Dr. APJ, right? And this is how we are trying to making machines to think like human being, and this is the starting point of machine learning. And with all this, machine learning can be defined as a computer program is set to learn from experience E. That means the historical data with respect to some class of task T, maybe prediction or classification, and performance measures P, because we have some historic data, say experience E, and we are going to do a task T. At the same time, just like that, we cannot do anything with the experience. There must be some evaluation metrics to validate, right? So this is the wonderful definition given by Tom Mischel, right? And this is the machine learning pipeline. So this entire pipeline can be divided into two. One is your data analysis part and the other one is data analytics part. So coming back to the data analysis part, gathering data sources. So data can be gathered in any form. It can be a hard copy, it can be a soft copy, it can be a click stream, it can be emojis, or it can be a memes, anything. And then do data analysis. So this is just a study about the data. What sort of data it is, what type of data it is, what is its summary, what is the min max values, and what is its mean standard deviation. Then after that, do data pre-processing, which means like cleansing the data. If there are any far extreme data points, remove that. If there are any missing values, decide whether to drop the records or to handle those missing values. And then comes feature selection, where you have to select the very important attributes which contribute more towards building a model. And this feature selection is very, very, very important. At the same time, it's quite interesting. And after doing all sort of pre-processing, then go for analytics, that is to make decisions. And for making decisions, we have plenty of models available which are categorized as supervised, unsupervised, and also semi-supervised. And finally, after building the model, just evaluate it with some sort of performance metrics related to those models, right? This is what the machine learning pipeline architecture. And the data analysis part, as I mentioned earlier, the data analysis part is just to identify the observations and then do investigation on the observations to get insights. For example, here a plot is displayed where in x-axis you have the number of ice creams sold and in y-axis you have the day of the week. And when you look at this graph, you can find that the sale of ice cream is high on Sunday. This is what the observations made out of this plot. And when you investigate further, the insight is Sunday is a weekend holiday, and people would like to go out and they'd like to have ice cream. So this is what the observation made out of the graph and the insights which we got out of investigations. And after this analysis, then comes the analytics part, that is to make decisions. So this is up to the ice cream seller to stock how much of ice creams on what day, right? So this is a simple example. And the machine learning algorithms are classified as supervised and unsupervised. And only a slight difference between this, right? In case of supervised machine learning, you'll be having the input as well as the output. And with that, we'll be able to make predictions. And if it is unsupervised, then there will be only inputs. With that, you can do some sort of identification or prediction. And better examples for supervised learning is your classification and regression. And for unsupervised, it is clustering, and it goes on, right? And in today's session, I have chosen the fundamental one, which is the linear regression, right? And so this is commonly used predictive analysis. And before entering into what is linear regression, how we decide whether this is a regression problem or a classification problem. For any machine learning, we need data, and data consists of two categories. One is your independent variable, and the other one is a dependent variable. And have to look at the dependent variable, and if your dependent variable is numeric, then it's a kind of regression problem, and if your dependent variable is of categorical, then prefer a classification, right? And this regression model is the fundamental one, and it is very simple, right? It is just a matter of equation of a line y is equal to mx plus c, right? And this model is to identify we have some set of independent variables which are called as predictor variables, and the output is said to be a response variable. And there are different terminologies are also used to represent this independent variable as well as the dependent variable. And in this session, I'll be using dependent variable and independent, right? So we'll be able to identify which independent variable is more significant for your regression, right? So that you can go for this linear regression kind of things. And these are the simple formulae where for a line you need the slope as well as its intercept. So to identify the slope, you have to find out how far your input variable x deviates from its mean, and your output variable deviates from its mean. The product of summation of product of that divided by the x minus x bar the whole square. And with that, you'll be able to find out the y-intercept, right? And here I have given a very simple data set which consists of only one input variable, say age, x, which is numeric, and the dependent variable is height, which is y. And so a number of instances are there. And finally, there is an input, say 26. Yeah, there is an input 26. So if there comes a person whose age is 26, what will be his height? This is what the prediction to be done, right? So before entering into the model, I'd like to show how the variables look like. And this is a scatter plot. The x-axis is age and y-axis is height. And this scatter plot itself shows that there exists some sort of linear relationship, right? And then comes the distribution of the data. So while data analysis, we have to look into the distribution of the data, because only based on distributions we can apply statistical methods for pre-processing as well as for model building. And for this data set, this is the actual plot of this data set, and this is the actual regression line. and the beta naught is calculated and beta 1 is calculated, and finally this is the equation, or this is the model, right? So the beta naught is 129.55 plus 0.35 into age. So as change in x, there will be change in y. And this is the unseen data where the input is 26 and the input 26 is substituted here. And sorry, I have used two dots, only one dot. So this is how the height of a person is predicted given age, right? And this is the predicted one. And our model predicts that the age, if person with age 26, his height is 138.65 centimeter, right? But we have to validate this model and we have to find what is the error rate, right? So yeah, this is how it is done, right? Here the age, here the height. This is the variance of x from its mean, and this is the variance of y from its mean, and this is x minus x bar the whole square, and this is x minus x bar into y minus y bar, and this is your y hat prediction. And here comes what is the difference between the actual and the prediction. So when you look at this, your actual output is 132, but your model says it is 136.6. So the actual output is 132 and our model has predicted it as 136.6. So the difference between these two is the error. So all the error terms and mean square error is calculated as 145.2403. And here it is very high, so we cannot claim that this is a very good model. In this case, there are certain remedies, like either you have to add more number of, that's the only way, add more number of data instances to get the error minimized, right? Actually, in this case, I have given only one input variable x. If there are more independent variables, then we can find out which independent variable contributes more towards the target. So that can be identified. Various methods are there. Through that, we can identify the best predictor and we can consider only the best predictor in our model, right? So this is the basics about regression. And for regression, there are plenty of metrics. I have listed some of them: mean square error, root mean squared, R square, and adjusted R square. So whenever we, actually this R squared is to find out the goodness of it. Whenever you add more independent variables, this R square value gets improved. At the same time, if you add a variable and if your R square is improved, then you cannot claim that your model will be good, or the variable which you added recently contributes more towards the output. It is not so. For that, we have to find out the adjusted R square. See, so this metric adjusted R square is the best one to find out the quality of any data attribute, right? And the challenges. Of course, all the machine learning models have its own challenges. And this linear regression, they are highly sensitive to outliers. There will be serious impacts if there are outliers in the data set. And it suffers from multi-collinearity correlation as well as heteroscedasticity, right? So this is outlier detection because linear regression models are highly sensitive to outliers. Here I have displayed the distribution of the input variable age, and this graph shows that this is not in a normally distributed one, and this is highly right skewed, right? There are two statistical approaches, basic statistical approaches. One is the z-score and the other one is IQR. And we have to prefer z-score if the variable is normally distributed. And this z-score is very simple, which is just say 3 standard deviation away from mean. So the values which lies beyond this 3 standard deviation away from mean are treated as outliers. At the same time, if the data is right skewed, then this IQR is preferred, which stands for interquartile range. Say for example, this is your data. This is your input variable. just sort this and find out the median. And actually it has got two quartiles, Q1 and Q2. So Q1 is the 25th quartile data and Q3 is the 75th quartile data. So the difference between this Q1 and Q3 gives the IQR. And for identifying outliers, we have to fix a lower fence as well as an upper fence. And this is the lower fence and this is the upper fence. And this lower fence is fixed as it is 1.5 times IQR away from this Q1, and the upper threshold is fixed as 1.5 times IQR away from Q3. So this is your Q1 and this is your Q3, right? So if any data points lies below this lower fence and above this upper fence are considered as outliers, and these outliers can be removed, right? So I have one another data set with a slight modification. Here the highlighted one, instead of 50, by mistake I have entered it as 500. Seriously, this is an outlier, right? So when we look at this age attribute, this scatter plot shows that this point is an outlier and this is the box plot, and here too it shows this point is an outlier. So rest of the things are same as the previous one. And for this data set, which consists of an outlier, its intercept is 142.13 and its coefficient is 0.01. So you can find the difference between the previous model and this model. And in this case, for the same unseen data 26, which is given as the test data, the height is predicted as 142.61, where in the previous case it was lesser, right? So this is how outliers seriously affect linear regression. So it has to be properly handled. Find out the distribution of the data and as per distribution, apply any one statistics method and remove the outliers and then go for building the model, right? And then comes collinearity. So this is an interesting situation. Unknowingly, all these attributes will be available in the data. Say, for example, actually this refers to situations where two variables are highly correlated. Highly correlated in the sense, say if you have height and say that the same age and height. As age increases, height also increases to some extent, right? So as age increases, height also keeps increasing. And here in this context, one is dependent variable and one is independent variable. And let us not talk about dependent as well as independent variables in case of this collinearity. Let us consider two independent variables, right? Say area of house and number of rooms, right? And we all know as the number of rooms get increased, the area of house will also definitely increase. So these two are positively correlated. So there exists a linear relationship. At the same time, they both increases. And in this case, we cannot make a decision or we cannot justify easily that among these two predictor, area of house as well as number of rooms, which contributes more towards the regression model. So it is not that easy, but there are options for that. Okay. So this we call it as redundancy. So redundant variables are there and redundant variables will also yield poor accuracy. So this redundant variables has to be identified and it has to be eliminated. And we have this Spearman correlation, Pearson correlation, such correlation coefficients can be calculated and then we can identify which are all highly correlated. And if you find any two variables highly correlated, you can drop any one. So dropping is one remedial measure for existence of this collinearity. And there is one another method, combining the variable. So when we drop the variable, we miss two informations or else we miss one information. So area of house will be there, number of rooms will be dropped, right? But there are ways where you can combine these two attributes and you can make them meaningful. So here comes another example for combining the variable. Let us consider weight and height. So if you have height and weight as independent variables, and if there exists a correlation between these two, and if you find that both are redundant, then you can do some sort of feature engineering where you can calculate this body mass index with this height and weight. So when you calculate this body mass index, and you can treat this body mass index as your one of the independent variable, at the same time, you can drop both height and weight independent variables. And now in this case, though we are dropping these two variables, height and weight, which are highly redundant, their informations are retrieved in the form of BMI. So this is one way of eliminating this multicollinearity. So, and then comes correlation of error terms, because after building a model, we have to look into the residuals, and there should not be any correlation among the residual terms, and there should not be heteroscedasticity too, and these two will give false results, right? So if there are if the error terms of the residuals are correlated, then the standard error whatever we get is kind of underestimated one. So it can be eliminated by means of some kind of transformations. Either you can go for transformations, or if it is a forecasting kind of linear models, then you can do differencing to remove this correlation among the error terms, right? And the other challenge in this linear regression model is heteroscedasticity. That is, when you look into the error terms, there won't be a consistent variance in the sense. So this is your model, and you have data points here. You have data points, you have data points, you have data points here, you have data points, and here also you have data points, data points, data points. So here, the error between this data point and the actual is less. At the same time, when you compare this, here the data point is this, and the it is to be expected at this point. It is to be expected at this point, but the actual point is this. So when you look into this, here the variance is high, whereas here the variance is less. So there is no consistent variance, right? Or else your spread will go like this. Your spread will be going like this, where the first half will have some sort of low variances, and the second half, or you can say the variances before median and the variances after median. So if the variances before or below median will be less when compared with the variances after mean. So such kind of heteroscedasticity should not exist in the error term. This also leads to false prediction. And the only way to solve this kind of problem is you can go for transformation. Either you can go for the basic things like log, or you can go for square root, or you can go for adding correlations. Even multicollinearity can be reduced using some regularization, like lasso regression as well as ridge regression. They too have the capability to reduce the coefficient, right? And once you reduce the coefficient, thereby your error term will get reduced. So whenever we do this regression model, we should be very careful about the presence of outliers in the data set, then presence of collinearity in the independent variable, and once that is done, then after building the model, we have to look into the error terms, where there should not be correlation among the error terms, and there should not be a non-constant variance or inconsistent variance of the error terms. So we have to we should have a control over all these things: outlier, multicollinearity, correlation, as well as heteroscedasticity. And one day after handling all these things, we can claim that our model is a better model, but need not bother about the accuracy and other things that can be improved in a different way. So with this, I'd like to conclude the session, and these are my references. So if you have any queries, you can raise, please. Any doubts you have or any queries? Any questions from the participants?